So welcome back to System Software. I'm going to cover Homework 17 right now. So let me take this and all right, so let's use the CodeGen so definition, program assignments, return value. So this was all covered in the last lecture on local variables and also the function implementation lecture. So these are the examples of the prologue, epilogue. Let's see what else I asked for.
Make it a little bigger.
Oh yeah, sure. All right, function definition, prologue, epilogue, assignments, and return value. So let's go through each one by one. Let's start with the function definition. So the function definition is done like this. Bless you. You have the pseudo-ops for the declaration, and definition is just a label. This is what the prologue looks like. It always looks the same for every function. And this is the epilogue. It always looks the same for every function. So let me start constructing the answer here. Okay, so for my func, this is the name of the function. I'll just copy assembly file metadata. And these assembly pseudo-ops. And the prologue. All right, here's the prologue. And here's the epilogue. It's all just boilerplate for the function. So questions on that? Questions on defining the function, the prologue, and the epilogue? Yeah. Do we need to push RBX? Yeah, why do we push RBX? Yeah. RBP is the stack pointer. But why RBX? Does anyone remember?
Preserves the value, right? You say new stack?
What's that?
The new stack?
No, it's a pretty, it's a very specific reason. It's just part of the calling convention that there are some registers that are caller preserved and some registers that are callee preserved. It's just part of the convention that some registers will be saved by the caller and some registers will be saved by the callee. So RBX is one of those that needs to be saved by the callee. Yeah.
The callee is the function call,
Right, the function being called. So that's all our push RBX is for. All right, other questions on the definition? There's homework 17. Any other questions on the definition, the prologue, and the epilogue? Yeah.
It's fine if instead of RBX I use RAX.
Well, RAX is, I think, not. Where's the API? So RAX does not need to be saved. So it's one of the scratch registers, so you can overwrite it. RAX is going to be your return value, so you will set it. Yeah.
And that's probably a really strict question, but we never mapped what R12, R13, R14, R15 B. Is there a reason why?
Oh, so
But I know those are preserved registers too, so wouldn't we also?
that's a good point. Yeah, so I think the reason I do this is that in some versions of this I would use RBX. So strictly speaking, if you don't actually use these registers, you won't need to save RBX. But we will eventually use them. We will eventually use RBX for once we get into operations. Yeah.
For future homeworks, presentation, I use the number one's register.
Yeah, yeah, you can use any registers you like. Yeah, as long as you preserve, you save them. All right, so that's the prologue and epilogue, and we need the assignments and the return value. So how do we save the return value? Yeah.
Is it the value into RAX, register?
That's right, yeah. We just save it into RAX, and RAX is expected to be written, the return value for the caller, the function calling this, will look in RAX for the return value here. All right, and then assignment is what I covered last time when talking about local variables. So let's see, we have these two, x equals 1 and retval equals x. And I covered these exact cases. So this is, we need to allocate the local variables. Yeah.
Question is why, I really said that as well. Is it okay if we do, instead of new dollar sign, the value into RAX and move that value into a register, into the stack thing, radials could do it immediately into?
Yeah. So I'm moving into RAX first and then moving it. But yeah, you could just move immediate into the memory location. Yeah.
About that one, would there be any cost to it, or would it be exactly the same thing?
It'll be fewer operations, so it'll be faster to do it the way you described, because you only have one operation. So that would be faster to do that. Okay, so where's the?
Is this code Gen 2 or no?
This will be used in Code Gen 2. Yeah, this will be used in Code Gen 2.
Okay, and when does it due? November 21st?
Just check the syllabus. I don't remember the due date off the top of my head.
Okay.
All right, so to allocate space on the stack, then remember the ABI, the local variables are stored here in the stack frame. So in order to allocate space for this, for the three variables that we have, so we've got var1, x, and retval, then we'll create space on the stack for these local variables. There are three of them. They're 8 bytes wide each. So we allocate space on the stack for these three variables. Does that make sense? Like pushing 3 times. Pushing 8 bytes 3 times. Yeah.
The substituting, or I'm pretty sure that's sort of substitute, right?
No, it's subtract.
Oh,
It's subtract. So this does
actually push the pointer?
this. It does RSP equals RSP minus 24. So it's just subtracting 24 from the stack pointer. So the stack pointer is a memory address. We subtract 4 from it, and that has the effect of taking the stack pointer, which is here, after we push, with RBX, and moving the stack pointer 3 8-byte slots down the stack or on top of the stack to here.
Does it have to be 24? Isn't it like 8 bytes per?
Well, why is it 24 in this case? Yeah. You have 3 local variables. So you could do more. You could if you know that. So there are. So this is like a simple scheme for compiling these programs. If you know these aren't used, you wouldn't need to allocate space for them. For instance, if they had different types, you might need to allocate more space. But I'm giving you just a simple scheme for managing memory on the stack, and that's just to give one entry of 8 bytes on the stack for each variable that you have. Okay, and then to do the assignment, the code is just here. I just gave you the code. So this is to do x equals 1. There's a couple ways to do it, as your fellow classmate pointed out, but this is one way to do x equals 1. So what does this mean? What does this negative 16 parentheses RBP mean. Yeah.
Offset from the base point.
Oh, sorry. Yeah. Yeah, it's an offset from the base pointer. So this is how you access RBP minus 16, that address space, using this. So this is moving whatever the value of RAX is into the address space allocated here. And the convention that I'm suggesting you use for the compiler is to just allocate the offsets sequentially for each variable. So var1 would be negative 8, x would be negative 16, ret val would be negative 24. Questions on that? Does that make sense? Yeah.
So we're just like going by like adding 8 by 8.
Yeah, subtracting 8. Yeah.
Subtracting 8?
Right, subtracting 8. Yeah, so notice that these are negative 8. So why is the top of the stack more negative than the bottom of the stack? You know what I mean? Yeah. The stack goes downward by convention. So the heap goes upwards in address, the stack starts at the top and goes downward. That way you kind of maximize space for both of them. Okay, so questions on this assignment? Okay. So the other assignment, which is given in class, is this. Ret val equals x is assigned to x. So this move copies, so what variable does this memory address correspond to? Yeah?
X.
This corresponds to x, and we copy the value of x into RAX, and then we move x into negative 24 RBP, which what variable does this correspond to? Ret val. Now these instructions I don't think could be combined into one. I think you have to do loads and stores separately. So you would need a temporary register to do this. And I think that's it. I think that's homework 17. Questions on homework 17? Yeah.
Is that move 10 to REX necessary? Or is that just
This is the return value. This is for the return value. Oh, sorry. The return value is not move 10 REX. It's so yeah. Sorry, I didn't do the return value yet. So how do we do return x? Yeah.
Negative 16 RBP plus offset RBP minus x.
Good. Yeah. So this is how you access the value of x because it's associated with offset negative 16 from RBP, and we copy it into RAX. And why do we copy it into RAX? Yeah, that's the System 5 ABI application binary interface for setting a return value to a function. Yeah.
So when we hit that return, it goes to that line, and remove the value x into RAX.
Yeah, when you see a return instruction in your compiler, when you write the code for the return instruction, you'll generate code that will take whatever variable it is or whatever number it is and move it into RAX. Generate code that will move it into RAX. So I covered this last time where, I mean, this is a different example, but if you recall, Antler is a parser generator, and when you input a program to your compiler, Antler will effectively turn this into a syntax tree. We talked about syntax trees several weeks ago, and it will traverse the tree for you. And those functions you're writing, enter and exit functions for each node, these will be executed, these will be run on each node, whatever type node is encountered when traversing that tree. Yeah.
One more question, going back to homework 17, would also, because we already know that due to the assignment, RAX has now the value of x, can we just return RAX, or would it?
Yeah, 100%. So what your classmate very astutely observed is that RAX actually already holds the value of negative 16. And so strictly speaking, you could save time by not doing that again. Yeah.
On that note, if you're talking about like a real like optimized compiler, would it not just simplify like most of this and just load one for the RAX return?
Absolutely, yeah. Actually, So a very good optimizing compiler would, first it would notice that for every execution of this function, x is always 1, ret val is always 1. And so you could just return 1. And then after that, it would notice that, well, these variables are never used, and just eliminate them. And so you could do this entirely that you could, an optimizing compiler would turn this into just move one into RAX, return. Yeah, 100%. Interested in how that works, take my class next semester or in the spring of any year, compiler construction. We go into actually the algorithms for tracking, doing register allocation, and optimizing in this way automatically. Yeah.
Already given at every function call?
Well, RAX is a register in the CPU, so all registers are available to all programs at all times.
Okay.
Yeah, this is the, remember from like CDA, maybe not everyone enjoyed that course, but so remember, this is assembly programming. In assembly programming, all you have is registers, and you have loads and stores from memory. That's all you have for data storage, without doing I/O to access like the disks and peripherals. But that's the storage you have available to you. So the registers are always available. The reason RAX is used is just by convention. So if different people are writing functions and they want to be able to pass parameters to each other at the assembly level, there needs to be some agreement because there's no naming. There's no return instruction like there is in C. So instead, we define conventions to interoperate with each other. I mean, just like if you go to plug in your laptop into a socket, you're participating in a bunch of conventions about like voltage and hertz, things like that. You don't know that, it's all set up for you, but because the electrical grid has these specific conventions, and they differ by country, the manufacturers know that they can follow that convention. This is the kind of crux of defining an interface. And that's why this is called the application binary interface, because unlike function interfaces, applications like APIs, which are written in a high-level programming language, the binary interface is the interface between machine code functions. All right, questions on homework 17? And also, I'm realizing I should be restoring RBX, which I'm failing to do here. Actually, I forgot to restore RBX, but let's hope that doesn't cause issues. Yeah. Oh yeah. So I asked this before. So move Q. There are like suffixes for different bit widths. So like 8 bits, 16 bits, 32 bits, 64 bits. Usually, the assembler will attempt to infer from the size of the argument. So RAX is the 64-bit version of the register. EAX is the 32-bit. It's the same register, but it takes the lower 32 bits. So if you don't put a suffix, the assembler will try to figure out the bit width for you. Intel actually has different instructions for 32-bit move, 64-bit move, 16-bit move, because of its backwards compatibility with its prior 32-bit and 8-bit, 16-bit processors. So just follow I'll always give you the assembly instruction to use. So just follow that, and then you shouldn't have any issues. Yeah.
Move is copying like the value into that register, right? Not like actually moving it.
Yeah, right. It's copy. Yeah, it's copy. Yeah, this is the mnemonic in the Intel world. But yes, it's a copy. It's not deleting this data somehow in the source register. All right, other questions on homework 17? Okay. So hopefully you have some sense of, so first of all, the ABI, how functions are implemented at the binary level, and the conventions that are used for passing parameters, saving local variables, and entering and exiting functions. Hopefully you have some sense of how a high-level language like simple IR or C, what it looks like in assembly, or at least an assembly version of that program that will be equivalent in its behavior at the machine code level. And hopefully you have some understanding from Code Gen 1, which I hope you've started, about what it looks like in a compiler to automatically translate, take this simple IR as input and automatically generate assembly code that is equivalent. And it just works by defining, just like we did for infix to postfix on our grammar-based translation. It just works by defining a snippet of code that should run on each node in your syntax tree during a traversal of that tree. So enter function will, so Angler will traverse the tree for you when it sees the function node at the beginning of the traversal. Your code should literally print this assembly code but substituting the name based on the name of the simple IR input program. And when Antler does enter call, your version of enter call should generate this code, at least for CodeGen, so far for CodeGen. We'll do parameter passing today, how that works. And same for return, and same for exit function. So questions on those three pieces? So when we write a compiler, we got to know the input language. We got to understand the behavior of the input language, understand how the output language works, at least for the subset of the language we're going to use, and also understand this concept of writing a program that translates between the two. So remember, our compiler is not trying to figure out the answer. It's not trying to figure out what the program computes. It's trying to generate a new program based on it that will do the same thing at runtime. All right, questions? All right, so let's go on to parameter passing. And this is the last and equally nitpicky part of this ABI. Parameter passing, it's a little bit of a pain. That's why I tried to make it its own lecture. But it's the last piece in our ABI. And once you've got parameter passing working, then function calls will work. And even more amazingly is that you'll actually be able to call C functions properly. And C functions will be able to call your simple IR functions. And hopefully I'll have time to show that at the end of the class, that once you get this ABI right and your compiler is generating code following the ABI, you'll be able to link with C programs. Okay, so let's get into the lecture. Okay, so just as a quick review, what's a function in this context?
Procedure.
Well, procedures,
A set of instructions.
yeah, set of instructions. It's a set of code, often has a name, and it has an input and output that's defined. How do we implement them? How do we make sure that local state works the way we expect with recursion in our C-like functions? The stack. We use a stack frame on each invocation of the function. And so we went over this many, many times, the components of the stack frame. Is it the caller or callee that sets up the green part?
Callee. No, caller.
Caller, yeah. So the caller sets up the parameters and the return address because the caller has that state at the time of the call. And the blue stuff here is set up by the callee. So this is what the prologue sets up. The prologue sets up the rest of the stack frame. And by convention, the green and the blue together are the stack frame for the function being called, the callee. This whole thing is the stack frame. These are just conventions. These are definitions. You could certainly design your own inner operation, your own ABI if you like. This is the convention that's used in lots and lots of machines, lots of Unix-like machines. So parameter passing, the way and local variables are there's space allocated for local variables in the stack frame by the callee. Okay, so how are parameters passed? So do we use registers or do we use stack for parameter passing in System 5 ABI? Anyone else? Let's get someone new, yeah.
The registers?
Registers? Who says registers? Who says stack?
Well, both.
Both, yeah, it's both. That's the trick. So it's passed through registers and stack. Could we make an ABI that only uses registers to pass parameters to functions for C-like functions? Yeah.
You need to limit the maximum number of parameters you could pass.
You would need to limit them. So in C-like languages, I don't think there is a limit, or at least not a limit that is restricted by the number of registers. And so no, if you wanted a C-like function with a unlimited or unbounded number of arguments, you would have to use the stack. You'd have to use something besides registers, because registers have a fixed finite amount. RAM is not, there is actually system-dependent bounds on RAM. That they're very, very large. But for most machines, the amount of RAM you have is far, far larger than the amount of registers you have. Okay, so in this ABI, it uses both. The old 386 ABI for System 5, the Unix-like world, actually wouldn't use parameter registers. It would just use the stack. And so this is one wrinkle of following the 64-bit ABIs, that the developers of this decided to use parameter registers as well, likely for efficiency for many functions. I don't know how they came up with 6. Maybe they looked at real-world code and said, 90% of functions have 6 or fewer. I'm not sure. But anyway, we have to contend with this so that we can follow the System 5 API and actually have interoperation with C functions. Okay, so I actually covered this already, kind of recover this just now. But local variables are created by allocating space. Oh, it's here. Local variables are created by allocating space on the stack. That's seen in the ABI here. You can see local variables being allocated on the stack here. Any questions on local variables? I need to close some of this. Too much stuff open. So any questions on local variables? Any questions from last time? Yeah.
How come in that example you just did, you went straight down to 24 and not like 8, or straight to 16, sorry, not 8.
Yeah, so why was x 16, negative 16, instead of negative 8? Yeah.
X is the second parameter given in the local var.
Yeah, we had 3 parameters. var1 was the first one. That's why. So in the convention I'm giving you, I mean, I think technically the function is free to use its stack space however it likes or not use it. But the convention I'm recommending you use is to just allocate these in order given to you. And this is actually why I designed the IR like this, because the local vars is declared right after the function, so right after the epilogue, you literally just count the number of these and then create a subtraction. Actually, I think I gave you code to do this already. Did I give you the code? I can't remember. But yeah, that's all it is. Okay, any other questions on local variables? And so what do we translate the name of the variable to in the assembly world? Because assembly world, we can't just use variable names. What does it get translated to? Yeah. Yeah, offset from the base pointer. Yeah, exactly. Okay, so that's local variables. Now let's go over how we can pass parameters. All right, so remember, the caller, the function calling you, and the one being called, they have to work together to agree on where this information is being stored. So the caller will pass these values via the registers for the first 6 parameters and then start pushing the remainder onto the stack, and according to our calling convention, in reverse order. So thanks to Brent for pointing this out. He actually implemented CodeGen 2 and pointed out that I put these in the reverse order. We always make these little mistakes. So notice here that we have 8 parameters here, A through H. H is the last parameter. But notice that H was pushed first. It's higher on the stack. It's higher in memory, which means it's lower on the stack. It was pushed first onto the stack. So in this convention, the last parameter is pushed first, and then the next to the last, all the way up to the 7th parameter. And then for the rest of the parameters, those get put onto the registers, these particular registers in this order. That's all just defined by the convention. There's nothing to learn here. It's just defined by the convention. Yeah.
Is this stuff processing the last parameter first?
No, not necessarily. It's just where they get put on the stack frame. So you can always use RBP with an offset to randomly access any part of the stack frame.
So how does RDP access the other parameters?
That's a good question. So how does RBP access parameter G? So we access the local variable with RBP minus 8, yeah. You do plus, yeah. You do plus. So these are pushed. So RBP is kind of in the middle of the stack frame. It's RBP is set to the entry that has the old RBP by convention. This is how our prologue is set up. And so if you know that the caller may use this convention, you know that it put the return address just before RBP plus 8, and you know that the parameters, any parameters, will come before that on the stack. So RBP plus 16, RBP plus 24, etc., for all the number of parameters. Yes.
So basically, like you want to put any value, you just add the value to RBP or subtract any value to RBP.
Yeah, so you don't actually have to do the subtraction yourself, so you can just use this special operand that x86 provides. You just put the offset here, and then in parentheses put RBP, and that will just happen for you. Yeah. So remember, registers are not RAM. Registers are physically separate storage units that are on the processor die itself. Whereas RAM is that, I mean, hopefully everyone here has opened up a machine before and seen physically where these components are. But the RAM is like a RAM stick, like a SIM or a DIM. I don't know what the technology is today. I'm not an EE. But it's a physically separate device that is on a separate bus and on a separate part of your computer. I mean, actually nowadays they actually are bundled together on like mobile chips. I have a PC bias here, but it is a physically separate device with physically separate storage. And did you learn about the memory hierarchy? You know, RAM versus registers versus cache, etc. So expensive, close to the chip, fast memory. There's less of that, all the way up to the disk, which is very large, very slow. And RAM is in between that. So, you have registers, cache, RAM, disk in the kind of current memory hierarchy today. And it goes from decreasing speed and increasing size. So RAM and registers they're physically separate things, and so I guess what kind of conflates this is that in the Intel world, the same instruction mnemonic, the same name of the instruction is used for both register copies and also stores and loads. So I don't know the right terminology, but technically speaking, in RAM you have stores and loads to put and get data. In the register world, I guess they're called copies to kind of distinguish it, but it's literally physically different hardware. And so registers are not in a stack orientation. They're individually named. You have a set of them. And RAM is just addresses. You have to tell the address. The whole point of maintaining RBP is so that these addresses will be relative to RBP, so that we can find them. Because we can't, unlike the registers which are named, we can't at the machine level name a RAM location in RAM. It's just a number we have to tell the memory bus to go do a store or load for us. Does that make sense?
Yeah, my question is, okay, so how does RBP access ABCD?
It can't access RBP because you can't, at least on this chip, the registers are not memory mapped. They're not addressed via a RAM memory location. They're accessed via just the number of the register. So this is like CDA stuff. So too bad they didn't cover that well. Don't know how else to say it. So you without going down to like the architecture numbering level, but the registers are numbered. There's a fixed number of them, and you can access them through instructions. RAM, you give it an address, and there's a separate little chip that will translate that address into some machinery that will actually go out to your RAM chip and either get or set the data on that chip. And it's numbered, a sequential number in byte addressed memory. It's the number of the byte in RAM. So I think it's probably confusing that in the Intel world you have the same name of the instruction. But this move immediate is actually a different instruction from this store instruction. So this is a move immediate. This is a store, which is also different from which is also different from this copy between registers. So this does not involve RAM at all. It's just copying data between two registers on chip. This is doing a store to the memory via the memory bus, and this is also just in processor. Does that make sense? Does that answer your question? A little bit. So
So how is the function able to use those parameters?
these parameters, just by the name of the register. So in the same way we can copy from RBX, So yeah, let me get through the parameters, then you'll see, because I'll actually show the code that we use to access these, and you'll see. These are just names of registers, just like RBP.
For code gen 2 or no?
We'll do this for CodeGen 2. That's right. Yeah, yeah. Okay, so let me actually show an example to show what this looks like. So just keep in mind, first 6 are in registers. The rest are on the stack, reverse order. Okay, so let's take. Let me see. Yeah, I'll put this example. Okay, so let's take this function here. It's called param test. It has 2 local variables, x and in-param. It has 1 parameter. That parameter is in-param. So notice that the parameters are a subset of local variables. So this IR design makes it really explicit that that parameters are also local variables, just like early C did. And in our language, when we designate certain variables as being in-params, then the compiler will generate code that will go and collect those parameters from the registers and the stack. Questions on this so far? Questions on the IR so far? So you declare what your local variables are, you declare which of those local variables are parameters, and then we just have code we saw last time, an assignment from the parameter to x, and then a return of x.
Is there?
Questions on that? Questions on that? Yeah.
Does this mean that you don't want to remove the stack pointer immediately after reading the load course? Typically, I imagine you're going to want to put in plan on a register, right? You don't want to grow the stack right after reading that line.
No, it's fine to grow the stack afterwards. It's fine. We'll see how it works. And here's a main that calls param test. So I just have argc and argv here for completeness. But it has one additional local called retval that calls param test with a single parameter, the immediate value 7, and it saves that result in retval. Okay, so I think I have this, having me starting with, yeah, okay. All right, so before we look into the assembly code, let's just see how the stack will be allocated from this call. So here's the same code. Here's our param test that takes in 1 parameter, assigns it to x, and then returns x. Here's our function, main, that will call that function. Okay, so let's assume main has been called already, and it already has its parameters and everything. All right, so remember our ABI. How is this parameter 7 being passed? Yeah, via register. So if we look at our calling conventions, RDI, the register RDI is what passes this value. So I had, oh, this code is a little different. That's not good. Okay, so we have the RDI register. What call first does is it sets RDI to be 7. And there's no other parameters. So what's the next thing that gets pushed onto the stack when we make the call? Return address. So here's the return address. And then we transfer control to param test. So param test does its prologue, which sets the base pointer RBP, the old RBP, and then allocates space for local variables. There's 2 here. So we have space for x and in param. And then the convention I'm going to give you for this compiler to make things really simple is we copy, the first thing params does is it copies all of the parameters into their local variables. So for register allocated ones, we'll copy this data into its memory slot for local variables. So the benefits of this, you don't have to do register allocation. You don't have to keep track of the fact that some variables are in registers, some are in local variables. Instead, you can just treat all variables the same, parameters and non-parameters. Then we'll assign x to in param. That'll set x to in param. And then for the return, we set rax to whatever the value of x is. So this is the full stack frame at the end of calling param test. Questions on, yeah?
How does it know, like, to put the 7 in those specific registers?
So that's what the when you generate the call, it will go through the list of your parameters and copy them to the appropriate registers. So yeah, so when we do this call, we'll take each of the parameters and copy them into the registers in the order as defined by the ABI. All right, so questions on this so far? Yeah.
I'm thinking this might mess with state, but why copy the actual value of the parameter and just
So similarly, pointers are just memory addresses. So there are no pointers to registers. Yeah.
RDI is pointing to the bottom of the stack, yes, or is it just
RDI?
RDI?
No, RDI has the value 7, which is what the parameter, value of the parameter. So if we're talking about pointers, the RSP is pointing here, RBP is pointing here. So this is the old RBP. Okay. So just remember RBP and RSP, those are the registers that will hold memory addresses. Those are the pointer. But the other registers we'll just use for data, well, actually, until we get to pointers. That'll make things even more confusing, but let's build up to it. All right, questions on this so far? All right, so let's look at what the code looks like to do this. All right, so let's take a look first at the code for main. All right, so here's main. So just like before, we have the prologue, we have space for locals, we have its parameter handling, we have, oh, this code is different. Let me get the actual code I have here for the. Oh, okay. I know why I know why I changed this. So I think my my grammar doesn't permit immediate values as parameters to functions. So it actually does need to be assigned to some variable first, and then, so apologies for that. So it's the same function, except we assign 7 to a param first and then pass it. So here's what the assembly looks like. So this is all basically boilerplate, our prologue, allocating space for locals. Okay, so this is our assignment from 7 to param. And here's our function call. So here's RDI. Here's the register that by convention should hold the first parameter, RDI. And so this is -32 because param is the variable that that holds the first argument. So we're calling param test on this variable called param. It's 32 because -8, -16, -24, -32. Its param is a local variable that has offset -32. And so this is how we set the parameter to our call to param test. Questions on, yeah?
So you always just do it to like the last spot, like of those four, if that makes sense?
The last spot?
So like if red dot wasn't there, would you do it at 24 instead of 32?
So this is just the offset of the local variables. So however many are here in the local var's declaration, this will determine what the offset is.
Yeah, that's kind of what I'm asking. So you put the param at the very last spot every time?
No, if I had reordered this and put param here, then it would have offset -24.
Okay.
Yeah.
Good question. I know that RC and C is on the floor.
I'm sorry, second?
So I'm trying to say, like, I know that RC and RB are two variables with different byte sizes. So
Uh.
how do you know it's going to be bytes?
So I'm making an assumption. So argc is an integer. It's supposed to be 32 bits. argv is a pointer, which I don't know the pointer width. What's that?
Shouldn't it be 8 bytes for RB?
Well, argv is a pointer to a list, so it's whatever the width of a pointer is, which I think can you do 64-bit? I think you can do 64-bit addressing. But at either rate, even if it's only using 8 bits, there's really no harm into allocating it into a spot with 64 bits. So I'm being hand wavy. I'm being like expedient here when handling these arguments.
And the project, our next one, project 2, would we be able to assume it's going to be only 8?
You can always assume all variables at all times are 8 bytes. It'll make things a lot easier. So we're not going to call like C library functions. We'll call C functions that we write that'll wrap library functions. It'll make things easier. But yeah, good question. Okay, so questions on how we set the parameter for our call to param test. So we haven't called param test yet. We're in main, and main's assembly code will set the parameter by copying whatever the parameter's value is into this RDI register. Why is it the RDI register? Yeah. Because it's the convention. It's the ABI. Okay, so when we have so this only has one parameter, this function, so we don't need to do any stack allocation at all. It's kind of the benefit of having register allocated parameters. We don't have to do any memory operations. And then once all the parameters are set up, we can issue the call, just like we did before in parameterless functions. And this will save the return address and transfer control to the param test function. Now, assuming param test is written according to the convention, it will eventually branch back to us in main and start running this code. So this is my very expedient code generator. This is adding 0 to RSP, so it does nothing to RSP. But if you have stack allocated variables, this will restore the stack pointer. So this is my lazy way of writing this code, so it works. So it's the same for every function call. But you could optimize this away by not putting the add. But here I'm adding however many stack allocated variables we have, the number of bytes to RSP. I'm adding 0 So it doesn't have any effect on this on correctness. So this is restoring the stack. There's nothing to restore, so it's add 0. And then finally, what does this instruction do? So we've called our function, and the next thing we do is we're moving RAX to some memory location. Yeah.
Would that be returning the value?
Very good. That's the return value. This is how the return value gets saved. Because remember, as I said, as I like harped on over and over and over, RAX is by convention where you store the return value in a function call. So when we're in the caller, when we're done calling that function, if we want to make use of this later and we want to save it and we have it, our developer told us that we want to save it. They want to save it into a local variable. An easy way to handle this is just immediately move RAX into whatever variable was asked of us. So this is retval. It has offset -24. So after the function call is done, we immediately save the return value, which is in RAX, into our local variable. Yeah.
Just want to confirm, so destination is on the right.
Destination's on the right. Yeah, an AT&T syntax. The destination's on the right. So questions on this? Questions on this so far? So we've got the parameter passing and the return value collection here. Yeah.
So does call not automatically save into that file?
No, call does not. You mean this call?
Yeah.
No, this does not at all. What does call do in the Intel instruction? What does it do? Yeah. Yeah, it saves the return address, pushes it onto the stack, and then branches. That's it. Does not pass parameters, does not save return values for you. That's all done via registers in memory, according to our convention for saving it. So for parameters, we pass the first 6 on via registers, and the return value we save via a register. So there's one parameter, and there's always one return value in our language. Questions on this? Okay, so that's how the caller works. The caller assigns parameters beforehand, and then after the call is done, restores whatever stack stack changes it made, and then saves the return value. So let's look at the callee, the function being called. So here's param test. So this is all boilerplate. This is the prologue and the definitions of the functions. This is, let me make sure I have the right function here. Here's our allocation of local variables. Okay. Here's our epilogue. All right, so here is the relevant part for handling input parameters. So there are lots of ways to implement functions. There are lots of more efficient ways to do it. I'm giving you a very, very simple schema that'll work for all functions, all types of functions. It won't be the most efficient, but it'll be the easiest, I think, to write the compiler for. So remember, we're in the callee now. We're in param test. So what param test does after it's set up its prologue, after it's set up its local variables, the first thing it does is to copy all of the registers into the stack frame space for their local variables, for the local variables. So remember, we created space for x and in param on our stack when we, in our prologue here. This is what the subtraction does. It created space on the stack for at least 2 variables. Here it's 24 because of the 16-byte alignment that this convention requires. But the first thing that happens after you have the prologue done is to just copy all the parameter data into their local variables. So why RDI? Why is it RDI? That's the convention for the parameters. And so that's why these two functions can work together, because they both agree on what parameter comes first. Yeah.
Why do we switch to 16 bytes from 8?
What's that?
Why do we switch from 8 bytes to 16 bytes?
For what?
I thought you said like we were doing 16 bytes instead of 8, like the line 16.
Because it's in param. X is -8, and then in param is -16.
Oh,
All right, so here's how we save the parameter in our call E function, in the function being called. Questions on this? Questions on this? And then we think we covered it before, but here's the assignment that we talked about last time, and this sets the return value. So this, if you look at our code said return whatever the value of X is. X is the first entry on the stack, the first local variable, so it has offset -8. And we copy that into RAX because why RAX? That's the convention, yeah, that's the convention. That the System 5 convention is to use RAX for the return value and RDI for the first parameter, yeah.
in this specific case, since we're just assigning X to in-param and returning it, why can't we just return in-param?
Yeah, absolutely you could. So this is the same question as like compiler optimization. So the real reason is that so remember, your compiler, you're not compiling a single program, you're compiling any program. And so it's much, much harder to write a compiler that will be optimized for lots of different cases. So you may have one where it's not this simple of a program. There may be computation. And so it's much easier to write a single compiler algorithm that will work for all cases. And so, and the kind of technique of doing this is to make very, very local decisions on each compiler function. So this is the function for enter return. In order to write an enter return that would know that X is the same as in param, it would need information that enter assign had. So it's much, much easier to write this, at least I argue, much, much easier to write this, making the fewest assumptions possible. Or I should say the strongest assumptions possible. The simplest assumptions, yeah. This one. So this I think is this is because the 16-byte alignment that the System 5 API requires. This caused me lots of bugs when I was writing the compilers before. But yeah.
That's not what I was asking, was like 16.
Oh, that 16 versus 24. Yeah. So this is like this 16-byte alignment. I have no idea why. I tried to look on Stack Overflow, but this System 5 API requires a 16-byte alignment. So if you push one variable, then you have to push and it depends on what's being pushed before, but whenever a function's being called, it's assumed to be on a 16-byte boundary. We have to maintain that. It actually wouldn't break here, but if you make other calls, you may break stuff. So I've given you that code to compute that, so you don't have to worry about that because it is really a pain. But yeah. Okay, so this is how we receive parameters, or at least one parameter, and write the return value. Questions on this? So hopefully this isn't too bad, right? So if we know that RDI is our parameter and RAX is our return value, when we make the call, we just make sure that we copy whatever data the developer told us they wanted, and they told us they wanted param to be the parameter. So we make sure that data is in RDI, and we can assume that the data for the return value is in RAX, and we can use whatever variable the developer told us, retval, to store that return value. Yeah?
Why are you adding 0 to RSP? What's the point of it?
So this, let's look at when we have multiple. So this is my expedient writing the same code for every input program. So some input programs will have stack allocated parameters, and this will make sure that stack gets popped, stuff gets stopped. So this really doesn't change any state at all. It's a wasted operation. Changes no state. Yeah. So okay, so that's our call. And so if everyone's following the same convention, call param test, the main function can assume that RAX holds the return value, and we can see that in our param test function, we assume that the caller has used RDI as the first parameter, and we satisfy its assumption about where the return value is by setting RAX. Questions on that? Questions? Yeah. So for the call, in this case, when there's a single parameter, by convention we use RDI to pass the parameter. So the caller, main, will store whatever value the developer asked the compiler to store. So it'll store the value of param. And we know where the value of param is because of our stack frame trick, or stack frame offset trick. And because we assume that param test is following the convention, we know we can retrieve the return value from RAX and store it in the variable that the developer asked us to store it in, retval. Questions on that? Everybody clear on that? And then inside a param test, because it assumes that main followed the calling conventions for parameters, we can use look at RDI to get the value of our parameter in param local variable, which is declared as one of the parameters. And to satisfy the convention for return values, we take whatever the developer asked us to return, the value of X, and save it into the RAX register.
And that's just the specification RAX? Like why RAX?
Because of the convention. That's the convention. So as long as everybody agrees on the same convention, it almost doesn't matter. It really doesn't matter what the convention is. What matters is that there is a convention that everyone follows. It doesn't matter whether it's RAX or RBX. This is the convention. And so as long as everybody's following the same convention, your function calls will operate as expected. All right, everybody with me? All right, so let's move on to a slightly more, or a more complicated example that has more parameters. And that's in here for the sake of time. I'm just gonna get, so this is an example I gave you for testing. So here is our, I have the full thing down here. Okay, let me show param test first. So this is a different version of param test that has 8 parameters, just like our calling convention example. So we have 8 parameters here. All it does is take parameter, the C parameter, copy it to X, and then return X. Questions on this code? Everybody good on this code? So it takes 8 parameters instead of 1. And we have a main function that looks long, but it's very, very simple. It calls param test with 8 parameters. It passes, it declares its own local variables A through H. It's just a coincidence of the same name. It doesn't matter that they're the same name. And it passes all of these when it calls param test. And just to make sure all these have a different value, which is useful for testing, we just assign each of these a different number, 1 through 8. So that's all function does. It just sets 8 variables, assigns them all a different number, and then passes all of these to param test. Questions on this? Yeah.
How would this work for something like Java if you use method overload?
That's a bit of an advanced topic, but basically the compiler will use its type system to figure out which version of the function to call. So at the binary level, they are different functions. And then it's just kind of bookkeeping to keep track of which one it is. And it uses the type system to figure it out, just like assembler does. So the assembler, it maps a move to a different actual move instruction. Okay, so let's look at the caller first. Let's look at main first. So all this stuff up here, this is the same boilerplate prologue, setting up local variables, etc. All the assignments. So these are all the assignments. So this is the relevant part here. This is the call. So you can see now, recall the conventions, RDI, RSI, etc. These are just the conventions. These are hard-coded. I've given you a Python list. You just hard-code those. And you can see that the first 6 parameters, so -32 is A, -40 is B, etc. These are all copies into those 6 registers. With me on this so far? So just like before, instead of moving just into RDI, we have 8 parameters. 6 of them go into the first 6 registers, to the 6 registers. Questions on this?
Those are the parameters, right?
These are the parameters. These are the parameters in parameters. This is the call to param test.
Mm-hmm.
So we're copying the main's local variables A through.
And the remaining 2 parameters will be pushed onto the stack.
Exactly. So the remaining 2 parameters, G and H, are pushed onto the stack. So this -32 is A, etc. -80 is G, -88 is H. And notice that these are pushed backwards. They're pushed in reverse order. And again, this is just the convention. The convention is to push parameters in the reverse order. I think it's just nicer that like G comes before H in the memory hierarchy. I think that's has a lower offset. I think that's why, but it's just the convention. So there's the push onto the stack. And this is why I had that add instruction. So after the call, the stack is now back. Because of the convention, the stack is now back to what it was before we made the call. So this add 16 will pop these two parameters off the stack. Yeah.
What would happen if, like, you had, this might sound a little excessive, if you had like 100 parameters? Would that cause like a stack overflow?
Probably not. Most stacks are set to be much larger than that. So if you had 100 parameters, there'd be the first 6 would be here, and then there'd be 96 pushes. And then it would be add 96 times 8. Yeah.
When there's push command, why is it negative and not positive?
So these are local variables, remember? So local variables are stored on the stack at negative offsets from the stack frame pointer. So this is saying push local variable A. So remember, local variables are translated into this offset argument, offset from RBP. And this is saying push A into the first parameter, or not push, but copy A into the first parameter slot, which according to the convention is these 6 registers in this order. Yeah.
Does the parameter setting in the function and not before the function's called?
This is before the function's called.
Oh.
Yeah, so this is the copy to the register passed parameters. These is the stack passed parameters. And then we do the call, just like before. And assuming the callee is following all the conventions, once it returns, we tear down the stack, we pop these two, which is what this add instruction does. And then we save the return value, just like before. So it's exactly like this example, except we have more parameters. All right, so let's take a look at what the callee param test looks like. So it's the same as its template for the prologue and everything is the same. But remember before we copied one register parameter into the local variable. Now we just do that 6 times for all of the 6 local variables. So here are 6 copies from those 6 registers into the corresponding offsets for the local variables. Questions on that? So just like before, we moved RDI into the spots for local variable. Yeah.
All those registers of the convention again.
It's all again to the convention. Yeah, it's convention. So because both the callee and callee have the same convention, we'll correctly have we'll have the correct order of parameters. And then for the stack allocated ones, it looks suspiciously like an assignment. It's just like assignment, except we're going from the positive offsets, which are where the parameters are, to our negative offsets, which is where our local variables are. We're moving the parameter, which is in a positive offset from the stack frame into RAX, and then copying that value into our offset for the local variable. Yeah.
Did you do all that in one move statement? You have to do 2?
Yeah, I think you do at the Intel world. I think you have to do a store and a load separately. I'm pretty sure. Try it, but I'm pretty sure you do. Yeah.
So for
Maybe I'm wrong.
inside the actual function call, does it take in all the parameters it requires in that function call, or does it just pick and choose whatever it needs to?
Well, for our compiler, we're going to do all parameters. We're going to do all parameters. For the ABI, you would have to do all parameters because there'd be no way of them knowing which ones are needed or not. Because you declared it to say these are the parameters, you'd have to do all parameters. Okay, and then so those are, and then it's the same thing. The return value is set, and that's it. So it's the same as this example, except we've got 2 stack allocated parameters. Okay, so take a look at CodeGen 2. CodeGen 2 is starting today. You can copy your code from CodeGen 1. Let me know, come to office hours if you have issues with CodeGen 1. Oh, Brent will cover, did he cover CodeGen 1 last week?
Yeah.
He'll cover CodeGen 2 tomorrow. So all right, everyone, that's 120. Take care. Thanks, everyone, and have a good weekend.
Bye, Zilla.
Bye-bye.